Well, here we go. The sample test for Unit 2 starts off with verifying a few identities. Justify each step using the proper code, beginning with the because symbol. Looking at the left side, I think by far the best way to go, maybe the only way to go, or the only normal way to go, is just to change cosecant to 1 over sine. And on the right side, we would change cotangent to cosine over sine. Cosine, you could write as cosine over 1. And that is justified by the reciprocal identity here and the quotient identity here. From there, we're just going to kind of look at the left side and multiply that together, and just like that, it exactly matches what the right side is, which means you're done. Number 2, you can start off very similarly. The secant you can change, cotangent you can change, and the tangent you can change, all by using reciprocal identities or quotient identities. This was a reciprocal identity, this was a quotient identity, and this was a quotient identity. And on the right, I don't really think it's ever going to change, so that is always going to be sine. It's all about the left. All right, what can we do on the left from here? Like, what do we see to do? Do you see how the bottom can maybe be added if you make common denominators, a least common denominator? So I can add to this, no pun intended, because I'm not adding, I'm just, what would it take to make common denominators? Well, wouldn't this need a sine to match the left, and then wouldn't this need cosine? So giving this denominator a cosine and giving this denominator sine, it'll make the denominators the same. And remember, whatever you multiply to the denominator, you also need to multiply to the numerator. So that's why this fraction becomes cosine squared over the LCD. And that's why this fraction becomes sine squared over the LCD. And as always, once you make common denominators, you just add the fractions together. All right, and it looks like the numerator is just staying 1 over cosine. Only really doing one thing at a time. So we get down to here, and then what do you see next? Well, I hope this cosine squared of x plus sine squared of x is just jumping out at you, screeching at you, that it's the Pythagorean identity. And again, going back here, this cosine squared plus sine squared is just a 1. And again, I don't think the right side is ever going to change from just being the sine of x. Okay, what can we do from here? I hope you look at that and see a fraction divided by a fraction. To be more specific, I hope you see something divided by a fraction. We're dividing by a fraction. How do we divide by a fraction? We multiply by the reciprocal. And from here, I hope you see that the multiplication, as we do the multiplication, the cosines will cancel, and you'll be left with sine. And finally, the left side will perfectly match the right side, and you'll be done. And again, this last step was because of multiplying and canceling. Number three. Number three. All right, looks like we have this 1 minus. You know what? The homework and quiz from section 2.1 is as I make this video, the homework and the quiz is like fresh in my mind. And this sample test problem is just like number 14, I believe, on the homework, and possibly a question on the quiz. I think it actually is like a question on the quiz. Not that you still have the quiz. You hopefully still have the homework back, but, you know. Anyway, here we go. So, this is looking at it going, well, maybe we can do the subtraction. 1 minus that whole fraction. If you're going to do that subtraction, what you need is to make common denominators. And so 1 over 1 becomes 1 plus sign over 1 plus sign when you give this fraction the same denominator as this fraction. And as always, immediately after making common denominators, you combine the fractions here by subtraction, and you get to here. And now what? Well, I hope looking at this makes you think of the Pythagorean identity, and when you combine it with 1 minus cosine squared, so this 1 minus cosine squared can be switched out with sine squared, so that's the Pythagorean identity. And now what would you do? And again, look, I never even covered the right side because I think it was always just going to be sine all the way through. So on the left, what can we do now? We can factor out a GCF of sine of x from the top. So that was justified by factoring out a sine from both sine squared and sine and getting this left over. So here's the GCF. Here's what's left over. And now I hope you see that this can actually legally cancel with that, and you're done after some canceling. So that, my young friends, is one way to do it. Or you could start it off like this. Perhaps you looked at cosine squared and thought to yourself, maybe I can switch that out with what it equals according to the Pythagorean identity. Because cosine squared is equivalent with 1 minus sine squared. But where would that potentially lead? What could you do next from here? Well, I don't know how much I addressed this kind of thing in class, but guess what? 1 minus sine squared can actually be unfoiled. Unfoiling 1 minus sine squared is exactly like unfoiling something like x squared minus 16, or x squared minus 9, or x squared minus 64. Or, you get it? It's the difference of two perfect squares. And so anyway, you can take 1 minus sine squared and unfoil it into these two bubbles, which immediately leads to that bubble canceling with the entire denominator. And so we're going to have some canceling to get us here. Oh, don't forget that it's 1 minus that quantity, which means technically this distributes, this negative distributes, so it'd be 1 minus 1 plus sine of x, and so we distribute the negative and we combine like terms of 1 minus 1, and we're done. Wow. Neato. So that was basically the test problems for section 2.1. But now let's get into the rest of the chapter, the unit. And number 4 says, find the exact value of this. Now, do not approximate. Now, we have our special yellow calculators. Keeping that in mind, I'm going to definitely need you to show some work. I mean, your calculator will, especially if it's in the proper mode, your calculator will probably just tell you this. All right? Or if not that, something equivalent, but probably this. Okay, probably this. So because of that, I'm going to need you to show your formula work with this being related to and very much comparable with one of the sum or difference formulas. All right? So looking at your formula sheet, you can translate this to all of this because of one of the sum or difference formulas. And then looking at your cheat chart, you can do the sine of 150, the cosine of 45, the cosine of 150, the sine of 45, and get all of that, which leads to that, which leads to your final answer. So feel free to double check on your special yellow calculator or whatever calculator you have. But show the work. Example B. Again, you need to train yourself and be ready for the fact that you might have to look at like the entire thing here as switchable with one of, according to one of your formulas. So, I mean, look at your sum and difference formulas. Cosine, cosine plus sine, sine. That can just be switched out with the cosine of 130, or this, minus the cosine of that, 10 degrees. So look, this whole thing can be switched out with this according to one of your sum or difference formulas. And 130 minus 10 is just 120. So all of this just boils down to the cosine of 120, which your cheat chart says is negative 1/2. Number 5, write the sum as a product. I wonder what type of formula you're going to use. I actually don't. The directions are like just giving it away. Sum as a product, write the sum as a product. I think you're going to use one of the sum to product formulas. And your first angle x is 6x. Your second angle for y is going to be 3x. And so this all gets thrown in here, but the only thing left to do for your final answer is 6x plus 3x is 9x, and 6x minus 3x is 3x. Number 6A, anyway. First wants you to figure out, at the end of the day, what they want is the sine of 2 theta. The sine of 2 theta, this is where you need to convert it or whatever, switch it out with what the formula says it is. So check your double angle formulas, because the sine of 2 theta or the sine of 2x, same thing, equals this 2 times the sine of theta cosinus theta. Well, in your original directions, you already know that the cosine of theta is going to be negative 12/13, but what is the sine of theta? Well, this is where you need to brush off your old Unit 1 skills and remember that you can take this as, well, I can say x is negative 12 and r is 13, and I can use the Pythagorean theorem to figure out that y ends up being negative 5, well, negative 5. So y ends up being negative 5. How did I know it was negative 5? Quadrant 3 is where theta is. In quadrant 3, y is negative. Henceforth, sine is negative. So now I know not only that the cosine is negative 12/13, but the sine is negative 5/13. And so multiplying all this junk together to get to a final answer, let me just do a little bit of, hey, just in case that helps. 2, you could think of as 2 over 1. And so multiplying all this together, it'd be like numerator times numerator times numerator, and then denominator times denominator times denominator. And the answer is overall positive, because it was like a positive times a negative times a negative. Part B. Well, so ultimately we just want the tangent of 2 theta, which you look at your double angle formulas on your formula sheet, and it says that it's this. So we just need to know the tangent of theta. Well, the tangent of theta last time I checked was y over x. So I guess you're going to need to still be able to recall that knowledge from your memory banks for the test. Right? The tangent of theta is y over x. So it'll be negative 5 over negative 12, which is overall positive. So positive 5/12. So you plug in 5/12 in for the tangent of theta, and we get this. And unfortunately, it looks like there's going to be a lot of cleanup. It's like, in a way, we've done the we've gotten over a big hump, I guess. And it seems like we ought to be done, but we are so not done. We just got to clean this up, right? When we square 5/12, we get 25 over 144. Because when you square a fraction, you square both the numerator and the denominator. 5 squared is 25. 12 squared is 144. And multiplying 5/12 times 2 gets you 5 over 6. Now, when we look to actually do the subtraction on the bottom, we can say that 1 is like 1 over 1, which is going to be 144 over 144. So when we think that, ultimately this needs to have the same denominator as this fraction, then it ultimately becomes what's in orange. 144 over 144 minus that fraction gets you 119 over 144. And so that leads to having a fraction over a fraction. More importantly, we are dividing by a fraction. So instead, we multiply by its reciprocal. And our final answer, after reducing and whatever, should be 120 over 119. Wow. So again, it was taking the tangent of 2 theta, looking at our formula sheet, changing it to this, because we were able to figure out what tangent of theta was. We plug it in, and so we got to here, But from here, there was like so much simplifying to get to our final answer. Hey, it is what it is. Deal with it. 7a. Once again, find the exact value. So, no cheating on your calculator. I'm sure at the end of the day, your calculator... Actually, I'm actually curious about that. I'm going to grab a yellow calculator right now. See what it says. If I'm in math print mode. So, here we go. The sine of 112.5 degrees. Oh, hey. It does not give you an exact answer. Not even in math print mode, apparently, unless I'm doing something wrong. So here's what we have to do. 112.5 degrees. That is certainly not one of our quote-unquote nice angles that we were working with in Unit 1. You know what I mean? So here's what we have to do. We have to rewrite 112.5 degrees using a nice angle or two nice angles. You know, we could think about the sum and difference formulas. If we could think of two nice angles that would add to 112.5 degrees or subtract to be 112.5 degrees, can you think of any? Of course not. We can't add two nice angles to be 112.5. How about the double angle? Can we think of a nice angle where it was like we could say 112.5 degrees is equivalent to 2 times a nice angle? No, that won't work either. But if we rewrite it as a nice angle divided by 2, that could equal 112.5 degrees. So that's what we do. We rewrite 112.5 as a nice angle that we like, that we can work with, a nice angle divided by 2. You know, because 225 divided by 2, last time I checked, was 112.5. So we can work from here. You know, this is going to be the same as doing the sine of 112.5. But this points to one of our half angle formulas. And now we can convert this using 225 as our x and change it to this. Because we can do the cosine of 225. The cosine of 225 is root 2 over 2. All right? So we get to here. And we do have to deal with this plus or minus business eventually. We could do it now. We could have done it even as one of our first steps. Like we could have done it here. But I think I'm going to do that last-ish. For right now, let's work on cleaning this up. Now, how do I usually do it? I take what's inside the radical here, this whole fraction, and I multiply the entire thing by 2 over 2. Which means, again, stay with me here, right, that this 2 distributes, and this 2, well, it doesn't really distribute, but it just multiplies to there. So on top, 2 times 1 is 2. 2 times 1 is 2. And when I multiply 2 to this fraction, this 2 cancels with that 2, and you're just left with root 2. So bottom line, root 2 over 2 times 2 is just root 2. And on the bottom, 2 times 2 is 4. All right? Now again, we still have yet to decide if this is supposed to be plus or minus, but you should also notice that Square roots of fractions, you can break it up separately, numerator and denominator. And guess what? We can do the square root of this denominator. So you do it. And so we still really need to do the square root of the numerator, which we can't really simplify or do anything more with. But we can just say the bottom is 2, just normal 2. And finally, the sine of 112.5 degrees. Remember, that's what we're doing. At the end of the day, what we're looking for is what is the sine of 112.5 degrees? Is that destined to be positive or negative? I mean, 112.5 degrees is in quadrant 2. Is the sine positive or negative in quadrant 2? It's positive. And that's why my final answer right here is positive. Okay? Whoa, what am I doing? Wrong way, moron. Ah, jeez. Number 7. The tangent of 195. Once again, 195, not one of our nice angles. So we have to rewrite it using one of our formulas, using a nice angle or two nice angles. One way to do it is to rewrite it as 150 plus 45, and that refers to one of our sum or difference formulas. And when you convert that, see, once again, your special yellow calculator will probably say something like this, or it'll say something, but it'll be equivalent to this. But we have to show some work, okay? You can't just cheat on your calculator. Or that, or actually, your yellow calculator will probably say something different, but still equivalent, and it doesn't make this or this any more wrong. But the bottom line is show some work. So this, by the formula sheet, converts to this, and then going with your cheat chart, the tangent of 150 is negative root 3 over 3. The tangent of 45 is a 1. And so, we got some ugly fractions within fractions. So we're going to have to do this to clear away Alright, so after cleaning all this up, you get what's in red, which is equivalent to what's in orange. Let's see what happens. Well, this is probably what we get if you were instead of rewriting 195 as 150 plus 45, you could also have rewritten it as 240 minus 45, which your, of course, formula sheet says to change it into that, which basically immediately changes that. So, how about this? You had at least a couple different options here to work with 195. Hindsight being 20/20, wasn't this the much quicker, cleaner way to do it? Because if you did it this way, you had to clean up this nasty fraction within fraction stuff. But here, just getting root 3 from the tangent of 240, you could have stopped right then and there. Okay? Getting to number 8. This is where we get into section 2.5. Solving for x. Solving trigonometric equations. Notice the interval that we want you to keep your answers within for x. And, number 8 starts off with a bang. We cannot just get the sine of x by itself as we would want. Remember, plan A is just to kind of get the sine of whatever by itself, or the cosine of whatever by itself, or the tangent of whatever by itself, so we could go directly to our cheat chart. But here we cannot just get the sine of x by itself. In fact, when you see this, in a way you should see this. Like back from your Algebra 2 days, x squared minus 3x plus 2. And if you were to factor this, you get that. So it's like we leave it equal to 0 and we look to factor. So we factor this just like we factor this. Let me get that. So let's let that sink in for a second. All right. Now what do you do after you set it equal to 0 and after you factor? Don't you always set the factors equal to 0 separately and then work with each equation independently? And now we can get the sine of x by itself by adding 2 to the other side and adding 1 to the other side. And once you get to here and sine of x is by itself, now you can go to your cheat chart. Now from here, the only angle you see is 90 degrees, which is true. And there's no double dipping here for sure. But you don't really see anything on your cheat chart that would say like the sine of what angle would equal 2. And there's a reason for that, because it's impossible. The sine of any angle, I don't care what angle it is, the sine of an angle can never be larger than 1. And on that note, the sine of any angle can never be lower than negative 1. So the sine of what equals 2, it's insensical, you know, if that's a word. Nonsensical. It's doesn't make any sense. It's impossible. So the sine of nothing would equal 2. It's too big. So no solution. So the final answer, x equals 90. Just one answer. Wow, just one answer. Number 9, the cosine of 3x equals negative 1/2. Well, we do not have, like it's already isolated, the cosine of whatever. So we can go right to our cheat chart and say, well, the cosine of what gets me negative 1/2? Well, so 3x would equal, from our cheat chart, 120 degrees or 240 degrees. So that's what 3x could equal, right? But because of coterminal angles, if you double dip on the 120, like if you just go around the circle again a full 360 and we add 360 to the 120 and we also add 360 to the 240, 3x could also equal 480. You know, the cosine of 480 also equals negative 1/2. And the same with 600. The cosine of 600 could also equal negative 1/2. But guess what? And also, if we triple dip, if we add 360 again and again, wow. See, it's like, I know 480 is too large for our interval, but that's what 3x equals, not what x equals. You know, and 840 and 600 and 960, because when we divide all of these by 3, even the 840 and the 960, the x value, like the answer for x, will be in our acceptable interval. So when you divide 120 by 3, you get 40. When you divide 240 by 3, you get 80. When you divide 480 by 3, bam. When you divide 600 by 3, bam. When you divide 840 and 960 by 3, yes, you get angles that are within our interval, and therefore there are 6 answers to number 9. Final problem, I believe. Well, in this problem, again, plan A is to get the cosine of whatever by itself if possible and go to our cheat chart. Well, we have a cosine of x on both sides, so we need to get them on the same side together. I'm going to subtract 2x from both sides, or in other words, subtract 2x over to the other side to combine that together. So 4 cosine of x minus 2 cosine of x is 2 cosine of x. Minus root 3 comes down, and now we've, now we're one step closer to getting cosine of x by itself. But now we have to add root 3 to the other side. And then what's our final move to get cosine of x alone? Divide both sides by 2. And once we get to this point where cosine of x is isolated, we can just go directly to our cheat chart to figure out what angles make this true: 30 degrees or 330 degrees. And that's it for what you need to know, or what problem, to be more specific, what types of problems you need to know how to do for the Unit 2 exam. Happy studying, as always.